I'm John Brisbin. I'm the lead of Reactor. I did say this is Stephane, and he is a consultant out of the London office. I work at home in Missouri, small town that I grew up in, and pretty cool to get to do that. But we are the main contributors, committers, the main manglers of code for Reactor, and then there's a small but growing community of very passionate people who really enjoy making people's lives miserable sometimes. So we all contribute to this project Reactor, we call it, but it's Reactor the library, but that's our Twitter handle anyway. And those are our Twitter handles. So kind of, you may have heard us talk last year or not, I don't know, but what I like to do is kind of keep it loose and kind of meta. So if you have questions, I mean, you can raise your hand. I may or may not respond, but if you don't want to raise your hand or interrupt, interrupt our wonderful thoughts we're having up here, then tweet to either Project Reactor a question, and we'll do our best. We're ADD, but we'll do our best to try and monitor that. And if there's questions that come up, we'll try and answer them, in the flow, because frankly, this is probably going to be a little stream of consciousness today. That's just the way we are. So you'll just have to keep up with us. I know it's early. So there's our Twitter handle. Get it handy. You can search it and keep it handy for later. But if you do have questions, try and save them until about halfway through, and then we'll kind of take a break and catch up. Yes. I know it's microservice year at Spring 1. I'm sorry. That's just what happens. You're going to be hearing the word service a lot, microservice, nanoservice. We'll make up a service. But the point is things are compartmentalized and they're service-oriented. They always have been, whether you call them event-oriented or, IOC and, separation and of various things. What you're dealing with are sets of services that interact with each other. You go.
Right. So the point John was just trying to make, in fact, is if you look at this sample commands, Unix commands, it's just interacting each other. The first command is just piping its result to the grep, and then piping to sort. Bear with me, there is a mistake in the Unix because I'm not that good bashing. You'll see there is a kind of similar concept when you have a microservice hosted on a website. You post some JSON request, but this site is itself coordinated to another site behind to grab a profile based on the JSON request. And this site is also coordinated with another site, for instance, NSA, because everything we say is just a CC to NSA. So that's another example of coordination, and a classic microservice could do this kind of thing. And if you think more about the pico-service, like very, very small, you will have a simple call, in fact, a simple service being calling another service, for instance, authentication. You authenticate a user, and when you authenticate a user, you generally need to hash the password, so this will call another service method. And after that, generally speaking, normally you find the username in the database and the matching hash. So this is another example of coordination between calls, basically. It can be commands, can be microservice calling another microservice, so it can even be just methods. All of that is just about interaction, and it's either interaction with the user or interaction with other services. The main point is, and what we're going to talk about in this session, is the boundary between these services, these components. So why the boundary is the real deal. When you connect services each other.
Stay back on that one. Yeah, that's important. That's important. I mentioned about services being kind of this all-encompassing thing, and we talk about microservices as being maybe a web deployed, or like they have some kind of characteristics that's unique to a microservice. But what we're trying to impress here today is that is only artificial And that's not actually what happens in reality. What happens in reality is you have disconnected components that need to interact across the boundary. And the boundary could be a method, it could be a network call, it could be a database, it could be a file. Somewhere or other, there's a component that has work to do, and it has to interact with another component, and we can call these services, we can call them microservices, picoservices, nanoservices, whatever services, and they cross this boundary, and sometimes it's a thread boundary, and so you have async work going on, and sometimes it's not a thread boundary, sometimes it's just a task queue, but it's still a boundary, they're still separate, they're still compartmentalized, and dealing with that transition from one to the other, that's a lot of what Reactor is going to help you do, because that's part of the whole reactive idea, you know, is that you respond to an event. So you have an event coming across the boundary into another service, and you say, oh, I have an event, I need to do something. And that's the essence of reactive.
Right, so...
but boundaries have threats.
Yeah, the thing is, as John just highlighted now, the boundary can cross a thread sometimes, or not, but when you call a method, basically you need to wait for the return value. And this thread basically has a name, it's called latency, and it's all about that. It's not about specifically performances, dealing with more messages per second. It's more about being responsive, being reactive, in fact. So I think here's a general rule. Humans don't really enjoy waiting normally. And the thing is, neither do the machines, because when you wait, what happens? A lot of things, in fact. And it translates directly to a loss of revenues for your project, for your company. Why that? Because humans first. They're not going to wait for your website to reply at some point for ages under a peak load. If there are a lot of users connected to your website, what's happening? What's happening is simple. The limited number of threads you have for serving these users are going to be blocked for maybe 1,000 users, 10,000 users. It depends on how you scale, how you load balance. But they're going to be sitting there serving these users, while the new ones connecting to your website are just going to wait for these ones to finish their request. So these guys are just going to wait for an answer, and at some point, they're just going to switch sites. This context switching is going to massively impact your visits on your site and your revenue. The other thing is, because you're basically waiting for a result on a service, it can be service to service, not user to a service, for instance. But if two services are waiting each other on each other, the thing is, another service can't call this service because this pair of services are already busy doing some work. So if there is a new request incoming, well, you can't fulfill it. So that's a bit unfortunate, because maybe your CPU has some availability. For instance, it's just used like 10% or 20%. It's inefficient, and you're not using your server. What happens in the end is you're going to spin off a new instance in Amazon, for instance, in EC2, and that's going to cost you money as well, because you will scale out first instead of scaling up. And that's the third point. In fact, this aggressive scaling is really really costly, in fact. And in the end, because this issue is going to come up in your Scrum meeting at some point, addressing this issue a posteriori is a kind of real difficulty, to be fair, because generally speaking, when you deal with that afterwards, you need a refactor, basically, so that's very costly. And the quick prediction, generally speaking, what happens in the end after these four things, normally speaking, you have your team mourning about how shit the application has become and it doesn't work as intended, and they leave and you have a super turnover, and that's also a loss of revenues because it costs money to train new people on your application, and etc. So bear with us, we're coming there. Now, one of the solutions to that is reactive programming. It's not the answer, it's a possible answer, so there are a few other answers possible. This one is quite popular these days, and we'll show you why. It's also, well, you can see in the name, reactive programming, Reactor. It seems to have a kind of relationship between them. It's also the buzzword of the moment, as I just said, and it's just a simple accumulation, in fact, of a lot of work across 20 years, probably.
That's an important thing to keep in mind, is that, you know, no matter what companies, and I'm actually not picking on TypeSafe in an indirect way here. I mean, they do a lot of stuff about reactive programming. Some very interesting information. They're extremely smart people. They work with us on the Reactive Stream stuff, which we'll talk about later. But they do have a tendency, and maybe this is marketing, you know, is to throw that reactive word around there, you know, and try and slap that on everything. And in fact, a lot of what we are doing already is reactive programming, event-oriented programming. You know, there's various terms that you can apply to it, but it is not something like totally brand new that was invented in the last year by some academic somewhere. This has been stuff since, I don't know, Smalltalk, I guess, if you want to look at it like that, that has been, you know, dealing with the issues of concurrency. I mean, when you know, computers were first being programmed and parallelism became an issue, these problems came up and they had to be dealt with. And at the time, you know, there weren't us yahoos around, you know, to muck things up. I mean, there was actually smart people sitting there and doing this sort of thing. And so they came up with some really elegant solutions, and then we forgot about them because, you know, that's old stuff, and we don't have to worry about it. So then we think, oh, this is all brand new. You know, it's not brand new. It is absolutely the accumulation of years and decades of thought and work that's gone into it. So this is as much as it may seem new, it's only new to you, and it's not new concepts that have been just suddenly reintroduced into programming.
Indeed, in fact, well, the diagram shows reactive programming is mainly event-driven programming, and generally speaking, event-driven programming leads to two things. Fault tolerance. First of all, fault tolerance is important because if one of your consumers, you know, you have this set of consumers reacting on events from a single source of data. If one fails, it's not the end of the world because you can have another consumer picking up the demand. Same for scalable. If you need to have more resources, if you need to use more resources, you can scale up or even scale out because event-driven is about decoupling the producer and the subscriber demand. And these subscribers, if you need 2, 3, 4, 5, depending on your peak load, you can just start kicking off some of them or some more of them. And if you need to elastically scale down, because you need to save resources as well, you can do that with this kind of level of indirection introduced by event-driven programming. And the two of them lead to what we try to solve there, which is low latency. Why that? First, because a fault-tolerant system is unlikely to impact a number of users in the end. I mean, if a user request fails, it's going to be picked up, for instance, by another consumer. So the user will not wait for a full cycle of spinning off a new instance or a new consumer, for instance. There will be already available a few consumers, and another one will pick up the request nearly immediately. Same for the scalability. The fact is, with this level of indirection, your consumer can run on another thread, which means, generally speaking, the publisher just returns immediately, basically, when it starts to call an asynchronous thread. Starting immediately to, well, it's just return immediately. It doesn't block on the return of the answer. The thing is, it's going to be a bit complicated to compose with that, because if it's on another thread, you will need a way to retrieve a result, or to say, after this method, I want to go to this method, and that's where the reactive stream and Reactor is heading now, in fact.
I did want to say one thing about this. You know, you see this arrow between event-driven and scalable. Well, that's not there's no guarantee that you're going to be scalable just because you make something event-driven. In fact, it could very well be that you would be much less scalable than you were because you didn't do event-driven right. So just because these are connected and that they complement one another and that event-driven facilitates fault tolerance and scalability doesn't mean that it's suddenly, with an event-driven application, you have an immediately fault-tolerant and scalable application. You have to pay attention to these sorts of things. Because if you think about it, and we're going to show you later on, one of the things that's a good it's been interesting to talk to people about this. They need something, if they're not into the reactive event-driven world, they kind of need some landmarks that they're familiar with, and just about everybody submitted a task to a thread executor or some similar thread pool situation. And so if you think about event-driven and asynchronous, okay, you have a piece of data, you have a task to operate on the data, but it has to work in another thread, so you submit it. Well, that's easy enough. But that doesn't mean that it's going to be scalable, because the question then becomes, when the task is finished and it has a result, what does it do with it? How do you communicate that to the next step who is dependent on that first task having been completed? In just a traditional asynchronous environment where you're using thread pools, you have to queue it, and then you have to correlate it because you have a request, and you have to create an ID, and then you have to submit it, and then and it could get very complicated and be very not scalable. So one of the things that Reactor tries to help you do is to be able to compose operations so that you actually are able to achieve those things that are possible through event-driven, but not implied just by its use.
Right. So one of the two massive rules of reactive system, as also highlighted on the Reactive Manifesto, yet another manifesto I know, is the first concern is to make sure that you split. You want to achieve zero bug killing, in fact, because the thing is, as I just said before, the consumer can be partitioned. If one fails, if it's on a dedicated resource, on a dedicated context, it will not impact the other one, for instance, the producer context or other peer context, like other consumers. That's important. And the scale-up and scale-out properties are by nature here because of the level of indirection of, generally speaking, having multiple threads help you to scale up on your CPU. If you have 6 cores, well, basically you can have 6 threads running in parallel. So that normally helps you to do more work at the same time. Same for scale out. If you have a level of indirection between your publisher and your subscriber, you can spin off new instances.
One thing real quick too, before we go on to the next, sorry. And we're just going to keep doing this. This is just, sorry. I did take my medication this morning, but this is just the way it is. Scaling is a multi-headed hydra. It's a double-edged sword. You can scale, quote unquote, by adding resources, but that doesn't mean you're actually going to scale the thing that you want to scale, which is throughput, which lower latency, right? You can shove more stuff at a system by using more threads and doing things, more tasks at once. But if you start passing beyond the thread per CPU, what you're going to be doing is making everybody run slower. So you might think, I can just shove a whole bunch of tasks in here and use a bunch of threads to do it, and all of a sudden I'll be doing a lot of work. No, you won't. Run a benchmark. I guarantee you, if you use a single thread or a few threads and you do a lot of work, you're going to get a lot more throughput. And we do this a lot. I mean, we run these numbers like constantly, and we get more throughput by doing smaller tasks with fewer number of resources, but do them so fast that they're in and out of the system and they're not bogging everybody down, and they don't get partway through their task, and then the kernel has to kick it out and shove another one in there to let it get its time in. And you can see how this is decidedly unscalable the more work you shove at it. So that's a thing to keep in mind. Scaling is not just throwing more resources at it. It's oftentimes reducing things down to a much smaller, easier to manage chunk that can come in and out of a system very quickly. And that's where the latency thing comes in.
So you may have understood already that asynchronous programming is core to reactive architecture because you fire off a request and you segregate the context. Also, functional programming is quite important because by nature, the functional programming languages are stimulus-based. You can chain logic and pass data around or pass even logic around. On the related topic, we're not going to dig into that yet. On the related topic, there is something called functional reactive programming. This one is even more owned by TypeSafe than reactive programming, so I'm not stepping in that in this way. But the thing is, Reactors, maybe a lot of things it doesn't do yet, but still there is something it tries to solve, and I think we do it more or less right. We solve the latency issue for you. So what is inside Reactor? First, there are synchronous dispatchers, and these asynchronous dispatcher or synchronous dispatcher, that's why we have synchronous, asynchronous in brackets. What it does is just doing the work like a task executor will do. And this is the main component used by two dependent components, which are an event bus, which we call Reactor, and the stream and promise, where we will focus a bit later on that one.
One real quick note on dispatchers. It's a term that we've decided to use in preference to others that we could potentially have used. And it's unique to task execution on other libraries because it doesn't focus on submitting to a pool of threads. A dispatcher is a dispatcher. It's like an event loop, I guess. And basically you can assign a dispatcher, and if you get a reference to that dispatcher and you pass it around, you're getting the same thread all the time when you send it because of the way that it works. And you can pool them, and we have a thread pool executor thing so that every time you submit a task, it gets a different thread. But that's generally not what you want. You want to, as I said before, you want to reduce resources. You want to send stuff to the same thing all the time. And that's, especially when you're composing operations and you're waiting on things to happen, you definitely don't want to be context switching every time you're executing a task back and forth in different threads. I mean, you're just going to bog everything down. So a dispatcher is like an addressable thread that has an internal task queue that you can just queue stuff on arbitrarily, if there was such a thing in the JDK. But there's not, so we had to create one. So.
And the slide before I was mentioning the functional programming as an important artifact of reactive programming, and it is. That's why, in fact, in Reactor we have a few functional artifacts. Some of them are even duplicate from JDK 8, but we need backward compatibility with JDK 7. We are minimum now we require Java 7. At some point, we hope to migrate to the interfaces from Java 8, but for now, we have our own. We also have this notion of tuple. Don't overthink that. A tuple is just a kind of CSV line represented in Java. And the timer, which is an important artifact of functional reactive programming, in fact, because sometimes you need to schedule a task later, sometimes you need to periodically repeat a task. We have this kind of thing in Reactor. And ad hoc to this main tree you see on the left, there is two additional packages, basically, of ad hoc utilities. So the first one is fast.io, which is a set of packages to help you deal with I/O, basically. So buffering, in-memory buffering, queues, persistent queues based on Java Chronicle, another awesome framework. It's optional dependencies. So if you don't use a persistent queue, for instance, based on Java Chronicle, well, you don't have to use it, and you don't include a dependency on your project. And a lot of codecs as well, because when you deal with I/O, generally speaking, you will have to pass the incoming feed, can be line feed, can be a byte array, a fixed length field, or this kind of thing. So we have all these utilities to deal with I/O, and if possible, in the most efficient way. And the other thing is the fast data packages. So we have, for instance, allocators. If you need to pre-allocate a number of objects, well, Reactor has some utilities to help you do that without, programming it yourself. So it's quite useful sometimes to pre-allocate a set of tasks, and that's what we do internally, in fact, because it saves you runtime processing of creating a new task every time, and GC, and that's quite impacting really demanding applications. For instance, Stuart was talking about RTI yesterday, and they've seen massive improvements switching from event to event allocation, which is generally speaking used by frameworks. For instance, in Spring Integration, you will wrap your message every time in the message, in the message object. And in Reactor, in fact, the event envelope we have in the dispatchers are pre-allocated on star. So we don't pay this runtime GC cost because every event are going to create this new envelope every time. And that's important thing as well. We've micro-optimized all this kind of thing to make sure that we normally overhead free when you integrate ourselves into your applications.
And it's not unusual to get an application that can run for what, days, weeks at a time without GC out, having to pull anything out because things just are, down to that level. We've looked at, we've profiled things until our blood's running down our cheeks because it's like, we're just trying to get the last little bit of, that microseconds there and, allocation savings here. And a lot of that stuff has been, put into some of these utilities, and they're just there for your use. The ring buffer is a good example of an allocator. We use it internally for dispatching tasks. It's something you can, it's like duct tape, but you can use it everywhere. And it really helps. It really helps with the ability of a system to communicate data to another one, especially when you're crossing thread boundaries, because you're always going to have this issue of how do I store this thing while I'm dealing with it, and then you can release it so that slot is empty. If we'll mention it later, but if you're out there on the Google right now, and you can do the LMAX disruptor ring buffer, and there's some really cool stuff on there that we use directly in Reactor, and it's one of the reasons that we can do what we do.
Yeah, indeed, because it's hard to do asynchronous programming, and the dispatching model really matters. A lot of things is going to impact your dispatching model. The context switching, the locking. If you use a queue, for instance, you will sometimes use a lock mechanism to avoid the concurrent writing on the queue. The message passing itself is hurting. Blocking, if you need to, if you use future, stop using them. And resource cost, for instance. If you think that creating 100 threads in a thread pool because your backend database is slow and you need a lot of connection, that also doesn't really scale, in fact, especially in Java.
And it's expensive because the more threads you add, and if you've ever profiled an application where you're trying to shove a lot of data through a thread pool, you'll find out that the thread pool itself is really pretty inefficient at high scale, creating future task objects that have to be GC'd, and then you'll see your GC percentage, just constantly trying to keep up with the stuff that's coming in, the tasks that are being submitted. And so if you think about, okay, now that's deployed on EC2 or somewhere where I'm paying for every single one of those cycles that it has to go through and collect all this crap that it created, then it gets expensive real quickly.
Yeah, so our secret weapon to do this kind of thing, it's not the only one, but this one is the main one that Seb mentioned, is a framework called LMAX disruptor, which initially is used in the financial industry, trading industry. These guys are real smart chaps, and they came up with all the most amazing optimization you can do on the JVM, like CPU cache padding, this kind of thing. Memory optimization, structure optimization, lock-free optimization as well. The message passing is often including a lock in your path. With disruptor, the ring buffer from disruptor is allowing you to pass a message from a thread to another thread without using a lock, which is quite good for the performances as well. And the message passing also, the way you pass the message is not necessarily by sending directly a message to another thread. It can also be pulled, which is what we see in message broker, for instance, like RabbitMQ. We send a message into a queue, and something is just keeping up behind, pulling, in fact, the queue. And that's good for slow services. But this cycle has a cost as well. So that's why we have also push patterns like non-blocking programming. And that's why we use ring buffer, basically. So because it doesn't use a lock, that helps us to just achieve a lock-free message passing. And functional programming is also important because with functional programming, you can add your computation straight after, naturally as a continuation after your main logic. For instance, you send an event to a method, a function in fact, but you want to do something after that. Instead of waiting and blocking for the answer, which is the future.get pattern, you just pass the continuation to function after the first function, and it will run on a separate thread, on the same thread. It doesn't matter, but the thing is, the logic is passed as part of the event, in fact, as part of the main dispatching. And before we jump into the stream, just a quick overview of how it does look like in terms of code. This is a Groovy slide because Java wouldn't have a fit in the slide, obviously, even with the lambdas. So Reactor has mainly 4 components required. The first thing is an environment, because you don't want to spin off a lot of dispatcher. You want to get them managed. As we said earlier, we don't want to create 10,000 threads because that is inefficient. So the environment makes sure that you reuse the same dispatchers and you can assign them to reactors. And the reactor itself is the event bus. So with a reactor, you can retrieve it from what we call builders. We have a lot of these builders, static builders, where you can pass method and chain. It's fluent builders. And when we retrieve the reactor, we can first notify, well, in fact, no, it's in the wrong order. The first thing you will do is listening for an event. So the first argument of the on method is a selector or topic selector, depending on how you want to call it. And it allows you to listen for a specific subset of events and react on them. And for instance, in that case, everything sent to welcome is going to trigger println hello name. And the payload comes from the notify method, which is the opposite, the publishing aspect of a reactor. You send to a specific topic, and in fact, there is a quick mistake there anyway. And you send a payload, in fact, event.wrap is going to be your envelope. In that case, you're not necessarily forced to use an envelope, but in that case, it can be useful if you want to attach headers. An event has a payload and headers property, so you can attach more context and more information to them. So
yeah, the mistake he was talking about was that just a copy and paste mistake here. In fact, we can just fix that right now. You actually just passed the key itself rather than the selector. Again, it's just it's a function of listening. The selector, there's different implementations of them. This is an object selector, which is you use a hash code underneath. It's fast, it's easy, if you're using for strings and objects and things like that. But you could use regexes, and there's a JSON path. You could put a JSON path in there so that when you do a notify and you send it a domain object, then it executes a JSON path and blah, blah, blah. So there's a lot of cool stuff you can do in there. But one of the things to keep in mind about a reactor is a fairly low level. I mean, on and notify, and there's some other overrides and various, combinations and permutations you can do with a reactor, but it's not a stream. It's not like a, multi-dependency, one thing to the next. We'll show you that in a minute, but just keep in mind, this is an event bus. It's like, it's like RabbitMQ. You send it messages and consumers consume them. You get it more complicated than that, you need to be using a stream. That's basically how, where it stands. Yeah, sorry. No worries.
A classic example of that is what, at some point when you start reacting on things like listening for things with the on method, or react by passing a function, like in JavaScript, you can do something, then you pass a function that will do something, and inside that will do again something. That's what we call the callback hell. And we have a classic example. Even Groovy couldn't save us from this callback hell in that case, because you can come to that very quickly. As soon as you reach a critical mass of nested callback, like you need to notify something, that will need to notify something else, that will need to notify something else, like the first level callback here, which listen on welcome, the second level callback listen to the talk topic, and there is even a dynamic callback listening on by and a constructed topic from the initial name. This kind of logic it can be quickly hard to read, and this is only hello world thing, When you have real production code in that, it's quickly becoming a nightmare, in fact. So when you reach that step, You can think about something else to play your events as a flow or dependencies, interdependent task. So that's what we call a stream. Yes, a stream. And this guy is going to help us understand what a stream is for the next slides now. So if we go back to the 2 previous slides, it was a nightmare. Very, well, if you read it really, which I'm sure you didn't because it's probably 9 by now, well, this is an exact translation of what I was trying to do. But if you pay attention to what happens, first I just declare a stream, which is like the reactor coming from a builder. And then I just declare my first step, which is a transformation step, map operation, transformation step, like enricher in Spring integration. Then you have a second step, chained from the result of the first step, because it's groovy, right? And the return of the tuple of in the first step is going to directly be passed to the second step. And then the consume operation will be your terminal step, terminal callback, in fact. And what you just need to do when you have this pipeline pre-created for you, it just then trigger some events, stimulate this pipeline, which is basically why we have a reference to the stream. This is the head of the stream, and we want to send Doge to the head of the stream so it can go through the first, second, and last step. So using a stream, there are a few use cases for a stream in general. The main one are composition and micro-batching in my mind. Micro-batching is what saved a lot of RTI, a lot of resources and improved the performances of RTI. So we have the micro-batching use case, we have the composition use case, embedded data processing because it's lightweight, it's not a fully fledged stream thing like Spark, for instance, where it can be distributed across computers, across machines. We're not there yet. So this is something, you know, Reactor is just a library with 1 jar, 2 jar with the dependency, and that's it. You embed that in your application using Maven or Gradle, and bam, that works. No, this is quite lightweight, and the stream itself can be declared in line as you see there. I just do a streams.defer, which is all I need to create a stream. I don't need a pre-declaration. It can be programmatic. It can even be at runtime on a request, anytime you want, in fact. Oh, sorry. And a common use case, and that's a use case used massively by Netflix, is the metrics and statistics. They use Hystrix, which is based on RxJava, a nice competitor as well. We come to that a bit later. And the feedback you can get from a stream quickly or attach new consumer to create metrics because it's super fast and inline, in fact. You can do that at runtime, and you can cancel some stream even at runtime, so you don't pay the cost if you don't need anymore some processing. This is really useful for metrics use case. So representing all of that is just to help you representing a data sequence. So what's a stream, in fact? It's just, it's just a pipeline where you will send from 0 to n element to it. It's not one element, it's not 0 or 1 element. It can be 0 to n element, it can be nothing, it can be n element. In fact, there is also a terminal state in a stream. You can even send a complete event to a stream to just say, okay, now I'm sure I'm not going to send any more events to you. Or you can also send an error, which is also a terminal state, unless you try to recover from it. An error is a terminal, terminal state, I'll just say.
One of the things that we do want to keep in mind when we're talking about a stream, and it's this come up before in conversations, is specifically I'm thinking of in dealing with a rat pack. We were talking with Luke Daly, and how do we send a response back via stream? Like if you have a service layer, and I'll show you in the demo how this works, and we send back a stream. There is a little bit of a question that is, and this is just kind of how reactive programming is I guess it's a side effect of doing it this way. But when you get a stream, you don't know how many you're going to get. You don't know for sure, not really, because it's a stream. It could be unbounded. So, but you can't definitely say you're only going to get 1 as a response. That's a promise. But with a stream, the intent is you're going to get some results. And when you get that stream back, you don't know how many you might get in the future. And when we get into micro batching and some of that other stuff, nano batching, pico batching, we're going to continue this on. You get into this where you could set a batch size, but you might not reach it. So you'll have to use a timeout. So there's some conflicts between keeping things moving through, being able to use the composition of a stream and kind of the arity of the responses that you expect back. Because in a reactive situation, it's every time you get a stream, you kind of have this question: how long do I wait for a response? Do I get 0? Do I get 1? So there needs to be some way, and this is not part of Reactor itself. This is just kind of something additional that you need to kind of communicate, with a service layer maybe in a particular way that says, well, I'm going to get a stream, but I'm only ever going to get 1 response or none. And that has to be part of your domain problem. It can't be solved generically, because sometimes that may not be the case. You may want to immediately transition. As soon as you get the next one, you transition to some state that says, okay, now I've gotten multiple results. Let's do something else now instead. So just a little thing to keep in mind that this is not completely straightforward. It seems simple, but it's not simple when it gets into practice.
Indeed. Often there is a mistake that people take a stream for a container, but actually beyond the state, like the complete or exception state you can find in a stream, it doesn't store elements. In fact, there are specific operations to let you store elements, but a stream is like just a staging, transient staging operation. You just pass something inside, it executes what it was meant to execute, and doesn't store anything. It passes that then to the next stage. And there are elements to help you buffer the demand, and we come to that. In Reactor, as we just highlighted, in fact, there is the Reactor itself, which is the event bus and the stream. So both can work great combined, because you can have a stream inside one of your consumers, and this can be an inline stream. And then if you have your event bus, you can still scale out, for instance, because the level of indirection introduced by a Reactor event bus is what you need if you need to scale out, for instance. But also the advantage of a stream over a plain event bus is the type check flow. So you really know what payload you're having in your stream. You can directly call operation programmatically. Your IDE will auto-complete for you, because it's all Java-based, and you can do that programmatically, basically. And as John mentioned, the publisher-subscriber control, if you need to depend on the publisher, if you need to change few stages, well, that's where you need a stream. Also, one of the biggest drawbacks of using a stream compared to a Reactor, a plain event bus Reactor, is a stream doesn't allow concurrency. We manage that for you, of course, but you can have at the same time 2 on next. We'll see what does it mean. 2 next elements reacting on a stage. If you remember the map example before, never ever you will see 2 times at the same time two threads going through the same operation, because that is forbidden by first the implementation, and also the specification we're discussing as well. So the rule of thumb is, when you see a kind of number of nested event bus call, just switch to stream.
One thing that I had in the demo, but I took it out because I felt it would be a little bit too complicated to kind of get into the whole issue. But you can use stream and event and an event bus together. You can use a stream and a reactor. And what I had originally done was create a stream and filter it, and we use a predicate whenever we filter a stream. Well, that predicate could be stateful. That predicate could internally listen on an event bus for different information coming in the environment and alter its decision about whether to let elements pass through the filtered stream, so that you don't have to recreate the stream. It would make it more efficient that way, and it would make your stream very dynamic. So you could not have to keep it in a map, or otherwise maintain some reference to this thing, this predicate thing that you have sticking out here, and that you would create it inline with scoped properly, so that all your variables are seen within your lambdas, and you don't have to have extra references anywhere. And then you just listen on the event bus for any changes coming in and evaluate whether you want to change your decisions about whether to let events pass through the stream or not. I felt like it was a little more complicated for a demo, but you can, I hope, kind of see how we're talking about a very dynamic situation here. It's not just a static stream with static logic, plopped in with hard-coded values and things like that. This is a very, very dynamic situation that you can create even within a stream, returning streams of streams, creating streams dynamically, listening on dynamic topics. That's part of the power of this reactive system, is that you have to be able to respond adequately to the events as they come through. And Reactor has to allow you to do that in different ways, and one of them is by using an event bus, or using some kind of event structure with a stream, which is a little more fixed and has more rules about how it's implemented.
So in Reactor itself, but a lot of the implementation or stream implementation, we have a distinction between two main kind of streams, what we call hot stream and cold stream. And that's an important thing as well, because it will define the way your stream behave. The hot stream is just a way to say, okay, this is kind of similar to an event bus. It will react on event generated at a time t. We don't know that in advance. For instance, a trade, a tick, or a mouse click, you don't know in advance how many mouse clicks the user is going to generate. That's what we call a hot stream. It's going to just come as soon as it arrives. A cold stream, in the other hand, is slightly different, because you can replay it. You can attach to it, and if you want to attach to it again, you can replay it from start. So a classic example is reading from a file, because basically you have the access to the beginning of the file. If you want to replay it, you can. It's already buffered for you. And Reactor helps you sometimes switching between a hot stream to a cold stream, and the opposite way. For instance, we have a buffer operation that transforms all incoming events into an array list. So collect basically all the events coming to this operation, and then the downstream element will consume this collection. So we can't switch from one to another one, but there is a clear distinction between them, and both of them will influence the way your stream behave.
One thing that we did get a question here on Twitter about the idea of concurrency and concurrent signals. So maybe we need to talk about that real quick, just to clarify what we're talking about. We support concurrency, obviously, because that's kind of a part of the whole async system. But what he was referring to was the specification declares that you're not going to receive on a given subscriber 2 signals simultaneously. So they're going to come in one after the other. They're never going to come in at the same time, which is part of the specification, and that's what he was talking about. Yeah, as far as concurrency goes.
We have a few examples, in fact, to show you how you scale up in that case. Because if you can't send more than one event at a time, like actors in an actor system, an actor won't receive more than one event at a time, because it protects the memory space it has. A stream is not that far from an actor, and in fact, the reactive streams, some of the aspects of the reactive stream specification have been influenced by this pattern. But we see how you can scale up anyway, because you can. It's not because it's a stream. You can't do concurrent. You can do parallelism. You can have multiple streams running in parallel doing the same thing. You can, in fact.
You just have to be a little more careful. We have to be careful about the boundaries that I talked about. So each functional composition there's a boundary around those, and so we manage the concurrency as events flow through. But you can do things in parallel. It's not a completely serial pipeline every time.
So it's time to speak about this specification in details. So the reactive stream specification is a simple way to define all of what we just talked about. In fact, it's about defining this stream and this communication between a producer and a subscriber in a non-blocking way, And from 0 to n element, it's not only one element, like a promise or a future. It can be from 0 to n. So that's the main thing defined by the specification. The other thing is very defined by the specification itself. All the implementation have, by specification, to be lightweight. They have to not consume a lot of resources. So we see a few friends, for instance, Rx Java and Akka Streams. By specification, they respect that, and they are very lightweight in memory in terms of runtime, overhead. They are all, very, not very demanding in terms of resources. Also, because it's a specification, it's also a protocol we can use to communicate between Reactor and Akka Stream or Rx Java.
And that's maybe not the use of the protocol, you think is like bits of data being transformed, being put into frames and things like that. Although we could get to that level, Reactive Streams really starts out with this idea of a protocol being more a conversation between two components, and it's not governed by the API. The API facilitates interoperability between implementations, and it gives you a few pegs to hang hats on, but the protocol, quote unquote, that you follow, the specification that you follow as far as the implementation goes, is based on this conversation that happens between a publisher and a subscriber, and since every implementation that passes the TCK follows that conversational pattern, then you know when you pass in a publisher to something how it's going to treat your publisher and vice versa. When you take a subscriber from somewhere else, if we take an Akka subscriber, for instance, we know we're going to treat it in the same way that Akka itself would treat it if it was dealing with it internally. Now, that's not always necessarily true. We might make optimizations for our own. So there might be, where we fudge that a little bit because we might want to, increase or reduce certain things that we might have to do. But certainly if we're going to deal with Reactive Streams abstractions being passed around, then we're going to treat it like the specification says, so that it's not just a shared API that we're doing. This is a shared conversation that we're having in the same language, if you will.
And I think one of, if it's not the most important thing about the specification, we know this pattern, event-driven pattern, for years, but what make it very different is, in addition to passing signal like data, like errors, like a terminate state, the incomplete terminal state, we have a new way to pass what we call back pressure or capacity. So what happens with this flow control is simple. We have a publisher in the, the publisher is a user controller, for instance. We have a subscriber, and we have this flow, classic flow of events going into the subscriber. But the async flow control is there to tell to the publisher, I'm ready to accept, I have the capacity to accept 10,000 elements, 1024 elements, whatever. I can consume that. And when I reach that point and I haven't finished to consume these 1024 elements, unfortunately, I can accept more. So what will do the publisher in this case, it will buffer all the incoming events. And this is really, really important. That's what makes it very different as well. This dynamic message passing optimization is called to the Reactive Streams spec, because if the subscriber has the capacity to accept new elements, it will push directly to hit. If it doesn't, it's automatically going to switch into a pull mode. It's going to drain a queue, for instance, rather than in a publisher, in the normal use case where the subscriber has the capacity, it will just pass the message using the ring buffer, for instance. So that automatic switch is making things very efficient. And you will see that we can expand that switch to a lot of use cases, in fact.
And if you think about when Victor Klang of TypeSafe got with us initially and proposed that we do this Reactive Streams specification and this kind of, this community, I don't even know what you'd call it, this, a collaboration, I guess. The example that he used was sending video frames, actually, in an application. So there's a situation where you have an application and you have a fixed amount of data. You know how long your video file is. You know how big each frame is going to be, depending on encoding and things like that. They might be different sizes, but still, you have some fixed amount of understanding about the data that you're passing. And then you know how many people are requesting video files be streamed. And hopefully, you also know the capacity of your network switches and the infrastructure you're running on. Well, if you know those things ahead of time, then you can say, it's not going to do you any good to try and send me more requests than I have network bandwidth to send you back video frames. So your subscriber could then say back to the publisher, well, I understand that you have a request, and here's how many I can accept. And that the publisher then could decide on it's based on the things that are specific to your application, and this you mentioned buffering. They can certainly do that, or but in some way you have to communicate then back. Maybe the publisher is also communicating this back pressure on back up the chain, so that you don't get into a situation where your publisher is trying to send data to a subscriber. It can't do it because it's limited by resources. You knew that ahead of time, but you had no way to indicate that to the publisher. And then what does the publisher do with that? Well, then they have to back up the train, all the way back. And so this idea of reactive streams is, you do have to continue this pattern on back to the client, and that's why I mentioned this idea of a protocol and being able to extend it into the client as well across as a network protocol. That's not part of it yet, but as long as you're operating within a system that speaks reactive streams, then this back pressure idea keeps bubbling back, and it's a conversation. It really is an interactive conversation between two components.
Can the publisher trigger the creation of another subscriber to take the extra load?
Yeah. We can.
Yeah, it depends on how the publisher is implemented. There's no, as far as what goes on inside those things, there's a few rules about how things should cross boundaries and how things should interact. But what a publisher does with the data and how it's how it adapts to changing environments, is basically, because we do things a little differently than ACA Streams might. Yeah. Exactly, and that was the example that was given originally when we started talking about this was that was one of the first things that we talked about, is that to get the full benefit out of it entirely from end to end, you're going to have to indicate demand all the way back to the client. But not everybody's going to speak reactive streams, so at some point you have to have a strategy that says, okay, I'm basically going to block until I'm not going to allow any more clients, or I'm not going to allow you to request anymore in whatever way is particular to that publisher.
If you think about the, for instance, a publisher, an HTTP server or WebSocket, if the subscriber doesn't have enough capacity, the publisher will basically behave this way. I'm going to stop reading the HTTP request. So I'm saving resources. I can give that back to another publisher, for instance. And that's really important. That's why this kind of automatic optimization or adaptive optimization, in fact, makes sense, end to end.
Yeah, there was another question, yeah.
You may be about to get to this, but I'm curious, when the subscriber sends an email saying, I've got capacity for 1024, does he block? Or does he he's just telling the publisher, I've got capacity, and the publisher says...
It's a callback system, so your subscriber tells the publisher how many you can take, and the publisher will send them to you.
But he's not.
There's nothing saying you have to send it to me within this amount of time, and that's where things could get rather wonky, because your subscriber could say to your publisher, give me 1024, and you really kind of overestimated your capacity a little bit, and so you could actually only take 512. But unfortunately, your publisher said, you know what, you told me 1024, by golly, you're taking them.
What happens if the publisher only has 3?
Then it sends 3.
And it will send 3 directly, but beyond 3, it will start buffering this demand. But also, you can drop. Sometimes it's useful to drop because you never want to overrun your system. You have a limited capacity, so you don't want to use your memory, so you can drop.
Yeah, like sensor data coming in all the time, like if you get to a situation where you're getting so much sensor data, maybe you don't need to collect it every 50 milliseconds, right? You'll be okay if you clear things out, and then whatever the value is at the end of that clearing of resources to accept more data, then you can go ahead and drop all those intermediate packets and it doesn't matter. You can't do that with a video file or some, or trades or some of these other things that have to be managed where you can't lose data. But that's dependent on the publisher and the interaction that you're having. Yeah.
So another follow-on. When a subscriber says I've got 1024 capacity, publisher says 3, does the publisher maintain a model of that subscriber and know that it has an additional 1021 slots? And if so, what happens if the subscriber then decides, oh, I only have capacity for 350?
If you say at the beginning you're getting so many, that's how many the publisher will give you if it has them available. And it's up to the subscriber to tell the publisher the correct amount.
Right, but if that changes, the publisher...
It doesn't matter. What you said originally is what's going to go. So that's why you need to be careful about it.
So the publisher has a model for each subscriber what its current capacity is.
Yeah, we come to that. It's, in fact, it's
Yeah.
specified by specification.
Yeah.
It's called a subscription. That's the relationship between a publisher
Yeah.
and a subscriber. And this model maintains this demand, it tracks the demand.
Yeah, we'll get to that, yeah.
Sorry. Well, we already said that in the follow-up questions. The subscription model, or this relationship between the publisher and the subscriber, is not a queue-based pattern. It's not only that. It can switch automatically to that, and that's the important aspect. But by default, it will be fast. And when your subscriber doesn't have any more capacity, it will be slower because it will switch automatically into polling mode. And well, that's a bit slower because you poll a queue or a link transfer queue or whatever. That's significantly, well, in terms of millisecond, of course, but relatively more expensive. So that's the driver, the main difference. So if we take the same picture, you can see in that case, the first subscriber is subscribed to the publisher and the demand is already flowing to it, and the publisher is already sending events back to the subscriber. And the thing is, it's a small capacity. You can see that because the arrow is thin. But if you can subscribe multiple subscribers to the same source of data, and sometimes they consume the data at a different rate. And the specification allows you to manage that because this one, for instance, is going to send more demand. It's going to say, okay, myself, I have the capacity to get all this data, so just keep sending me more data. The other subscriber is going to maybe buffer, maybe drop the data, but this one is going to take all the incoming data as soon as they arrive, for instance, and that's a completely accepted behavior. So having this kind of system of demand passing to the publisher, in fact, inverted demand, allows you to do a kind of interesting things. For instance, again, used by RTI product, you can do batch publishing, or you could do what they call micro-batching. Why that? Because if you know that your subscriber, which in the case of RTI is Gemfire, if you know that Gemfire can only the optimization we have analyzed is it can only accept 1024 elements in all scenario to do a put all operation to send that to a distant server, a distant Gemfire server. If you know that in advance, what you do to the original request, to the original publisher, which is a TCP server, you will say, stop reading if I'm beyond the 1024 elements, because you don't need to do that. You can do that for all the thing, all the protocol, but for myself, don't do that. It's worthless. I'm not ready to accept it. You're just going to queue up. And that's optimization. That's optimization of memory. That's optimization also of network bandwidth, because when you tell that in advance to a publisher, instead of sending elements by element, you can collect them into an array and serialize that into a single shot instead of doing that for each element. So knowing this demand in advance is a lot more efficient in general. And what happens is, if it's hot stream, what happens is the demand, the next elements are going to be the ones you see as soon as you subscribe. Take the mouse click, for instance. If you attach a new subscriber to a publisher, and you were clicking before that, and that produced the element into this publisher, you will see the mouse click only after you subscribed. Well, that's normal because that's outstream. You can't replay unless you declare it that way, but by default you can replay what happened before. Physically, it's impossible. You can go back in time unless you specify it and you transform this out stream into a call stream using buffering, for instance, a buffer operation. Like a call stream will be able to send the same data, the same element to each of its subscribers. You have a file publisher, you subscribe twice to this file publisher, well, you will replay the data from the beginning because you have access to the original data. Physically, it's possible. And what's not specified by the specification, and that might confuse you at first, is a transformation. There's no transformation such as map, filter, distinct until change, all these kind of operation attached to a stream, generally speaking as well. All of that are not defined. The specification only defines what we just seen now, which is the contract between publishing and subscribing. But there is an important interface to allow you to chain operation called a processor, which is defined by the specification. A processor is both a publisher and a subscriber. You can think it as a function or method because it accepts data, it's a subscriber, and it also produces data to the next element, so it's a publisher. And we define this interface, so that helps us. If we were talking to RxJava, for instance, we are the publisher, they are a processor, and AkaStream is a subscriber. Because RxJava is a processor, it will accept element from ourselves and will send that to AkaStream, for instance. So that's the interface, that's all about the processor. And then, in each of the implementation, for instance, if you take RxJava, they will implement processor on observable, for instance. This is where you define the operation. So we have stream, they have observable. I don't know about AkaStreams. Ratpack has stream as well. We all have different implementation. So
20 minutes. Yeah, go ahead.
Go ahead.
We'll go through this real quick, and then we're just getting down to a few minutes. We got demo to do and whatnot. So
yeah, right. So
we won't get to the demo. I'll just show you the code. You saw it last night. I pimped it out a little bit, and I was going to show it off. That's okay. We'll go ahead. Go ahead.
But it's important. Also, I think we prefer to have an interactive question, so we don't lose the track of what happens. So, right, there are streams in Java 8, and that might be all confusing because they're also called stream as well. What the hell is going on with these streams? So the streams coming with the Java 8 support are slightly different, in fact, because this is mainly focused on transformation, and in fact, the main difference is as soon as you declare an operation, it's going to fetch. And unlike a pipeline you declare in Reactor or a stream, every time you call this nice, for instance, transforming a collection to a stream, we'd get the stream. Every time you call a filter or map to int operations, they're going to be called. And sum is going to, for instance, in that case, block until the sum is actually finished. So there is no what we call the dynamic switching between a pull and a push, and it's quite what it's fetching. So that's a main difference. It's not the same, and that's why Douglas from behind, in fact, the all sorts of asynchronous services you find in the JDK, like Solid Executor Service, is part of the specification, helping us to define this contract. Why that? Because Oracle is already thinking about including what we're just discussing now in JDK 9. The other thing is, RxJava mates, they do great stuff. Plus, they are from Netflix, the cool guys, you know. So why do we have something else? It seems like RxJava in itself is kind of a standard, which is not far from truth, in fact. But there are, and that's why they are also part of the spec, there are differences as well with what we just defined now. The first thing, well, RxJava is all about reactive extensions. You know the Microsoft paper about this reactive extension defining 10,000 functions, methods, transforming method, in fact. It's super complete. I think either ACA-Stream or Ratpack or Allself won't compete in terms of coverage of operations. They have all the operation you can think about. If you think about something, they have this operation right now. So yeah, they have a really, really important set of operations. It's event-driven, and they have on next, on hero, and on complete. And they have the flexible scheduling as well. You can attach a specific dispatcher or scheduler, as I call it, to a stream. So the stream is going to be run on this scheduler. And that's the issue, and that's why they are also part of the specification. Unfortunately, they don't have this notion of dynamic demand, so they can't overrun a subscriber, basically. That's why they needed to attack this issue as well. What happened in the case is you can subscribe, but you can say how many elements I want. So basically, it will subscribe to everything. And if you don't have enough capacity to do it, yeah, you can do things in parallel, like using buffer operation and stuff, but by default, you will overrun your subscriber. So yeah, the main issue, demand all data. And the other streaming tech around, there is ACA, we just mentioned it, Storm, Allself, Ratpack, which is a new player as well. The semantics compared with Spring integration patterns, also it's less complete and less academic. The main difference is if you wanted to implement reactive streams with Spring integration channels, you will have basically to implement 5 different channels because you will need 4 for the signal you will see now and 1 for the opposite signal doing the demand. So it's possible, maybe we do that, and we maybe have to do that at some point, but there is no direct relationship. So who's joining this party? A lot of people, in fact.
Yeah, it's and of course, we wanted to fill up the slide, so we threw everybody on there. But not everybody is as equally involved. And some have given a little bit of time, and some just don't really have a whole lot of time to spend on it. But these are all the people that have expressed interest in this collaborative effort at a specification. It's not a JCP. It's not meant to be like that. It's a bit of a committee-ish type thing, but it's very democratic. There's got to be basically one representative of 4 of the companies to +1 on something for it to be merged, et cetera. Things like that. But to really kind of get going, TypeSafe initially came to us, and they talked to Red Hat guys, and I don't know how far along they are, but I know that of the people that are actively working on implementations at Netflix, Twitter, TypeSafe, obviously, ACA Streams, ourselves, Ratpack, there's various people in the community that are on board with this. And the specification is nice because it's a fairly short document, reasonably short. It lays things out. It's very reasonable. We don't demand anything that's unreasonable of libraries. And so it's actually relatively easy to create an implementation. There's only 4 interfaces and 3 that you only need to worry about.
So what are the end purpose? We just discussed that before, but if you can see on this slide, there are 4 different players, ACA, Ratpack, RxJava, and Allself. The thing is, with this nice system, everyone can communicate each other, the demand and the signal, and that's very neat, in fact. If you see that, what does that mean is no one is going to be impacted by latency because it's all propagated correctly between each of these players. And you can see each of these guys fits a very nice sweet spot. ACA has a very nice distributed system, ring-based. RxJava has all of this ecosystem about metrics, historics, for instance, etc. We have this kind of bridge with Spring Data, for instance, on all sides, and we do have a lot of data-oriented operation as well. So we all have a kind of sweet spot. It's not like we're overlapping all the time each other,
Yeah, I think I think it might be beneficial. We'll just take a look at. We'll just take a look real quick at the demo code, and like I said, it's what you saw last night. So, but I did change a few things here and there. And when we're talking about Ratpack and the web stuff, you can see that it allows you to create a very succinct expression, if you will, of how a HTTP request is to be done, and then we go off into this service class in our update method, and this is where we get into the streaming part of it, in that we say we want to do an update on something, And here's where we're getting our dispatcher, which means we're load balancing across the available dispatchers we have because we're doing blocking I/O in the very next call. The location save method is a repository method that we're calling on our repository. Spring data, nothing that we've added to it is plain Spring data repository. Here's that broadcast next call that says, I'm observing elements that come through, and anything that comes out of the save method then gets broadcast onto the global stream that other streams are listening from. The JavaScript, I won't go into it because it's actually longer than the Java code that I have to do the server side, but it basically opens up a WebSocket connection, and in Rat-Pack, because Rat-Pack is implementing reactive streams, and because we understand how to speak with it, I can, in a single line, connect my service layer to a WebSocket and then call map on that so that what comes out of my service layer gets immediately transformed and sent on. And Rat-Pack knows how to do that. Rat-Pack knows how to request information from me, and I know how to send it to them, so that all I have to add in my service layer is I'm getting the find one, so I'm looking it up. I'm doing a blocking operation, which calls a repository method and returns a value. And I'm flat mapping, which means I'm going to flatten a stream that's coming back out of this transformation step. I'm actually going to merge the global event stream that everybody listens to, that all events from everyone who updates in this app gets dumped into, and I'm going to merge in what I find historically, because I may have missed events. And this is what we were talking about earlier. You can't go back in time. That's true, but you can merge a stream of historical data with live data and have it all kind of, because you're never going to get, simultaneous notifications, it's all going to come in as if it came in either live or historical, either one. And your transformation functions don't care. They're, in this case, they're completely non-blocking operations that operate in memory. And there's the predicate part that I talked about, which could be a stateful component. I could, inside of here, actually listen on use other resources. This is a simple operation because it is only calculating, doing a mathematical calculation, but it might be more involved than that. It might have to look up information. And if you think about that for a second, that's interesting, because if you have a filter on a stream that has to go look up information, how would you support that in another way than composing functions on a stream of data, especially if you have to do it in a blocking I/O operation, which means go look up information out of a database. You would have to ensure that this gets operated on the right thread, and then we go back to what we were talking about earlier, correlating requests with responses and queues and blah, blah, blah. And so since we're using ring buffers, for task dispatching, it's extremely efficient to send information from one step to the next. And then I can, to be fair, probably it's a single statement because there's only one semicolon, but there's really two statements because this merge is a separate thing. I could put a return in front of it and do other work inside this flat mapper. But this is critical because it's a good observation to say, well, what do I compare this to? I mean, this looks nice, this is succinct, but what would I have to do in a traditional imperative approach to achieve this behavior? Well, you tell me. What would you have to do to support multiple blocking operations to make sure that they're operated on asynchronously from how the Rat-Pack server is going to be sending the data back out to the client, because it uses Netty underneath, so it actually has to go get the specific event loop that your channel's listening on, and it has to transfer events that happened or originated from your thread onto its thread and go back out to the client. How would you coordinate that conversation? How would you interact with the component that was doing that? You'd have to have a lot more than just a few lines of code to do that, and this is really where everything kind of comes together. The composition, the functional approach, stream-based data, tasks, dispatching, all of this kind of comes down into the ability to create an extremely succinct. This is a WebSocket, it's a REST and WebSocket app. And it's a single bean method inside here. I'm using model mapper, so I don't have to have set set this, set that to do mapping. I'm using Rat-Pack for the web. I'm tying my service layer directly, so I call a service method which returns a stream. I'm just doing transformations on it in different contexts, and that's extremely important because here I have a reference to my location service. I'm actually calling a service method. I'm creating a stream, and then I am tying that into another stream that I'm getting from data that I got out of the first stream. And all of this stuff is able to just kind of flatten out and compose from one to the next, so that you don't have this, this spaghetti and callback and a callback hell as we were talking about earlier.
The important aspect as well is in the few lines you see, none of these lines are actually blocking, so you return immediately to the request. And Ratback, which works on top of Netty, will be able to serve new requests quickly. In fact, that will happen at some point, and because we use this nice thing from Ratback, kudos to Luke Daly for that, we can render at some point. We have suspended the request, and the then is going to be the rendering. Shall we close up with the few resources? Yeah. Right. So I'm going to quickly show the mapping, and after that we close and conclude on the resources with John. That's the main artifact from +1, which is subscription, but in blue, that's the main artifact defined by the specification. And also, we are in orange, and we implement the specification this way. We have a class stream implementing a publisher. We have an action implementing processor, so remember that it's both a subscriber and a publisher. And also we have a promise, which is also a processor, but only accept one element because it's a promise. The protocol is quite simple. You've seen there are a few signals. So we can start directly in error mode. For instance, the publisher declaration failed. So the first event you will receive when you attach a subscriber can be on error. Or if it worked, it will be on subscribe first every time that's specified, ordered specified. Then a multiple on next, maybe 0, maybe 10,000. And then it will finish at some point, eventually, it's not necessary, it can be a live stream of data, with an error or with a complete state. So it's quite simple in terms of protocol. I mean, it fits into one line. So that's good. Yeah. I'm going to, that's our reminder. So we can conclude on that. So we have a few ways to declare streams. That's one way to declare a bit like observable. Sorry, I went a bit fast. So we can create a stream with an environment and say, OK, I will stream in this stream 1, 2, 3, 4, 5, and I will subscribe whatever I want. For instance, identity processor, which I can declare here. I'm not going through completely, but that's a kind of vocabulary you can have in Reactor Streams. You can declare an action and combine it so it becomes a black box, and you can subscribe it. It creates a processor out of 10 lines. It will transform that actually in one action. You can subscribe directly to it then. No, let's skip that one. But I will do that anyway. So, thank you. Well, in this one, we can just keep a few seconds on that. John explained it, but the flat map is not a really, really complicated thing. I mean, it's a stream sending data to a substream, and you want to get the result from the substream into your mainstream again. It's just like a fork, if you want, a fork join. So nothing more. And you can see in that slide I send a name, I observe dynamically, I map to much monad, and in the end, on the mainstream, I do asat it much monad. So I receive the event declared, in fact, in the subflow. We need to also keep a few seconds for that, because we were talking about non-concurrency in signals. Actually, you can if you use this specific operation, which is parallel operation. This parallel operation, in fact, will accept data and round-robin broadcast this data to up to 8 different streams, which actually will be on 8 different dispatcher, 8 different threads. And actually, you can see that the next operation map don't receive the data, but receive a stream directly. That's a bit functional, I know. But on this stream, in fact, you're going to have 8 of them in that case. On this stream, you can create your flow, and you can see necessarily that's going to be the same flow. So you will consume upstream data concurrently in that case.
And this would be handy if you wanted to add inside the lambda that we have here in the map. Maybe you want to add a little bit of a counter for doing some partitioning and add a filter. And so the stream that you get back, you could filter out any events that would potentially go to streams on other threads based on, some hash code %8 or some logic like that to very succinctly create a parallel processing, fork join, whatever term you want to attach to it.
You can connect to the demo. which is
Yeah, let's show the GitHub page there
Yeah.
so that people can if you want to look at the code, run it yourself. You can run it locally. The idea behind the demo, as I showed last night, was that you would have multiple screens entering data at the same time, and you would be able to see those updates actually happening, and it would put it on the map for you. And it's all really cool, and you know, Ratpack's awesome. It's got Rave.js in it and JavaScript, which I'm not a JavaScript guy. I didn't really enjoy that part of writing the demo, but you know, it's there, and you can make it prettier, and it should be a good example of some of this stuff, even though it's deceptively simple because it's just a few lines of Java code to do a whole lot, admittedly.
Indeed. So we can jump to a few links, few conclusions, a few things, in fact, few things. So basically now we are only mainly for implementing the specification and passing, well, RxJava is on the verge to do that, but passing the TCK, our Ratpack is really about to do it. I think they're maybe doing that right now. I'm speaking now, in fact. That's the main frameworks implementing the spec. So what does it mean? We've seen that already. We can communicate each other quite easily. They have all these links. Well, you will have a chance to assist. So you see 0.4.0.m2, which doesn't really impose kind of trust. But why are we not switching yet to? Why are we not switching yet? You'll see the resources. Why we're not switching yet to 1.0.0 is we were waiting for at least 3 passing implementation to start the 1.0.0 specification process. Now with 2 completely passing the TCK, Aka Streams and us. But as soon as RxJava, which is on verge, as I just said, in September or October, they have an announcement probably, or Ratpack pass completely the TCK, I think we switch to 1.0.0 mode. But the specification itself, you know, it's 4 interfaces. The jar contains 4 interfaces. It's not going to change, basically, but the TCK may change. And also, currently with 2.0.0 build snapshot, we're really about to release the 2.0 M1. If it's not today, it should be this week. The 2.0 M2 will come later this month, and the release comes end of this month because we have to be. We want to be aggressive on the cycle more than we used to be in this year of existence of Reactor. We want to be more aggressive on this release. So early October, you will think about that again. The work in progress is new stream operation, ecosystem upgrade, like making sure that we speak nicely, Spring integration, Spring XD, for instance, or Spring Boot, or Spring Data, whatever, or on ecosystem, because we have the very chance to work with all these heroes from all these Spring frameworks. So we make sure that works nicely. And new starting guides as well. It's open to contribution. We are very easygoing chap. So if you want to contribute as well, just be part of this nice thing, I think. If you want to add anything?
No, that says it all. I mean, we exist by community contributions, even though, I mean, we obviously spend a lot of time putting into it, and real applications, I mean, real production applications that are running, you know, millions of data points through them in a day, millions of data points through them. So this is not like, you know, slideware stuff. I mean, this really does exist, but it will only get better if we have people that are willing to contribute with it. Not just contribute issues, although you can do that, but you know, if you can send us a test case and a pull request, that'd be even better. There was a question right here, yeah.
Where is that shared spec at?
reactivestreams.org. Get the GitHub site right there. Reactive Streams. Just that contains the
point the link to reactive-streams.org. It's easy. It points to all the things behind.
Yeah. Any other questions, real quick, on the end? Yeah.
I mean, like, this may sound like kind of a dumb question because
No dumb questions, only dumb answers.
I'm trying to summarize your presentation, but it seems like what you're saying, and this is a godsend if this is true, is that if I kind of grok the compliance suite and I grok the 4 interfaces, then I kind of get for free an understanding of Reactor, Aka, Ratpack, at least a
Bingo! Give the man $100. Yes, that is correct.
We've been spending months like
You win.
various frameworks and points, how is
Exactly.
what's it
It doesn't matter anymore because you can use observables where they're important because Hystrix uses them. You can use Reactor because it's got cool stuff. You can use rat-pack and you can tie them together, and they all talk together. And there's roses and rainbows in the world from then on. Okay, maybe not the last part, but certainly they could talk together in fewer lines of code with less stuff that you have to write. Did you have follow-up?
Yeah, I had a follow-up.
Okay.
Which is, like, promises are a really important part of everything that I've seen.
Right.
Is promise just a singleton set of...
Yeah, we cheat. We basically take a stream and we say, okay, expect the first one. That's what you get, and that's a promise. But that's what it is. I mean, it's a stream of arity one, a promise. It exists in either, pre-complete, complete, or on-air states. It's very simple. Okay, anybody else? Yeah.
So, how to, from a testing point of view,
Yeah.
testing a reactive framework,
You test code? Why would you have time to write tests? I don't have time to write tests.
we are using reactive framework, but
Right.
testing is like, we are not even 40%.
Yeah, we've got several hundred tests, and they took a long time to write, and it's
Game
not
is code.
easy. It's not easy. I guarantee. I understand async. Tying things together, you count down latches. Blah, blah. There's sometimes there's just no way to get around it. It's just got to be ugly. But we do. If you go into the specs, we use Spock in all of our tests. Even though part of our stuff is Groovy, all of this the core is written in Java. But there's a whole lot more tests in Spock than there are plain Java. But if you go in there, you'll see kind of how we set up an environment to do asynchronous testing and to make sure that we get results we expect. And then with streams, it's actually pretty easy because you don't care about any of that stuff. You're just dealing with the composition of functions at the end. But if you're doing asynchronous event handling at a raw level, then you're going to have some external synchronization, countdown latches, things like that will make sure that your test goes like you expect it. But there's a bazillion examples in the test. I mean, there's literally hundreds upon hundreds of tests to show how we do that testing internally.
Good. I think we can wrap up.
Yeah, we got to get out of here. But if you want to come up and ask questions,
Cheers. Thank you.